Right, okay, I better get going. I've got quite a lot of slides, a little bit of a warning, and most of those slides are actually going to be quite detailed. Now, what I'm going to say is don't try and not get too fussed with the detail. The whole point of the detail was basically there so that if anyone wanted to come back and try and apply some of this stuff afterwards, they would have the detail there to go and do that. But I don't think it's actually at all necessary to understand what the message of the talk is. So I'll try and highlight what the important bits are. And anyway, so I'll be going through these quite quickly because I've got quite a fair bit there. So what is this all about? So what I was trying to do was look at the Clang tools, in particularly libtooling, and see if I could build a sort of a refactoring tool, because you see all online of how do you use the Clang tools to build stuff, and you get a sort of a simple example that's something like printing out the number of functions, and I wanted to sort of say, okay, can I actually take that, build on it? Would it actually be practical for anyone else in a different open source project to actually come and use? Why might you want to do this? That type of thing. So basically what I wanted to do was, how was it actually feasible for a non-expert to do this? And then basically present what I found out, and then sort of try and simplify the boilerplate that if anyone else wanted to do it themselves. Okay, so why might you want to do this? I think there's about 3 realistic ways that you might want to do this. If you've got a very large code base and you want to apply a refactoring across the whole lot, and you don't want to type it out manually, and your code base is sufficiently complex that you can't do it with something like spatch. I think something like spatch would be very, very good for C. I don't know whether it would work at all well with C++, or whether it even will work with C++. And something like the Clang AST means you can apply these things very, very accurately. If you want to introduce your own domain-specific errors and warnings, now this is something that I think some of the major web browsers have done. What they've done is basically say, okay, I see your class here. It's got a inline constructor and it's got 10 arguments. Did you really want to do that? So it's things like that. If you have sort of your code base with unwritten rules, you might actually be able to write a plugin to detect some of that. And then there's the sort of an FFI generator or a serialization tool. So quite often doing that for C++, quite difficult. So Clang tooling gives you the ability to basically get the parser for free. Okay. So I'm going to go through what is Clang very, very quickly. Don't want to dwell on that too much. So Clang is actually built from a composition of libraries. It's not just a compiler, which means you can build your own tools by just including bits of those libraries. And it's actually been set up so that building refactoring tools is fairly simple with a relatively small amount of code. I mentioned a compilation database at the end. That's basically where it can capture all of the command line options that you do in a typical build, because a lot of these tools, you can have macros that can change the behavior of your code as it goes on. So any refactoring tool has to take account of those macros. I won't mention those anymore because they're very easy to look up how it's done. So Clang's got 2 APIs, C API and a C++ API. The C API is basically designed to be stable, mostly used for things like an Emacs-like IDE to query for things like where is this token defined, that type of thing. But it doesn't give you the full amount of control that the Clang C++ API gives you. And the C++ API is just what Clang is implemented in. The downside of the C++ API is it's deliberately not stable. It's basically the Clang developers reserve the right to change it at any time. So if you build anything with the C++ tool, don't expect it to work in the next version of Clang. If you provide a plugin, it's not going to work on the next version of Clang. You basically have to keep rebuilding to match the latest version of Clang that you're using. So that does introduce some deployability problems, which I'll hopefully touch on later. Okay, so I'm going to, yeah? Yes, Max?
Thank you. The API, does functionality get removed from time to time?
I've never seen functionality being removed. It's mostly just they find a different way to do things and they decide to change all the parameters. It's mostly simple things. It's not generally anything particularly big, but it's enough that if your function has been renamed, then you plug it in the next version of Clang, it just won't link properly. Anyway, so we're going to use the C++ API mostly because I can use the AST matches, which is what I think makes actually writing the tool feasible in the first place. Okay, so again, one of the lessons from this talk is don't try and learn the Clang AST. It's huge. It's hundreds of classes. There's no common base class, which means that you don't, when you're actually traversing it, you don't say, here's a node, get me the children, go to each child. You'll have something like an if statement where you can say, okay, get me the if part, get me the else part. So you can't easily write a generic routine to just recursively transfer through the whole thing. You have to use the sort of inbuilt visitors. The other important class that we'll mention here, AST context, that's sort of a class that goes with that, and that sort of controls where all the source locations is. So typically what you'll find is you'll use an AST matcher to find a particular node, and then you'll use the AST context to actually find the details of where that node is. Okay. So first thing, very, very quickly, this is kind of just for the sort of tutorial and bits at the end. There's multiple ways of getting Clang. What I've used for this one is the mono repo, which is kind of the way Clang is going to move towards a single Git repository with all of the individual bits in. You can get all of the individual bits like Clang, LOVM, Clang tools extra from SVN or Git, but it's a little bit more work. So the other thing to do is, are you going to use an in-tree or out-of-tree build? So what an in-tree build is you're basically using Clang's own build system. So you're basically just hacking a few files inside of Clang, introducing a few new ones, and just tweaking it a bit, and then just using Clang's build system. That's by far the simplest way to go. If you want to sort of basically manually include files and libraries, you can do that, but that's just a little bit more work than I wanted to do this time. Okay, so I'm not going to go through this at all. There's a link, LLVM Get Started guide. All that I did for the in-tree build, created a new directory for my various plugin. I called it Clang YVR18 just to be very imaginative, and just set it up to get to the various libraries that I needed. Now, to get the libraries there, I had to learn via link error, and I then had to learn by basically copying. So quite often when you go into doing the Clang tools, you're basically learning by example. You're saying, finding something that's doing something similar to what you're doing, and then finding the extra bits as things go on. One of the things that you won't see in many online tutorials is this word private, which is new. If your CMake file fails for a weird reason, it's probably because you've left out the private, because one of the online tutorials hasn't got that in. It's again, it's a CMake detail. Won't go into in there now. Okay, to actually build the tool, this is just some lessons that I've learned from building Clang many times. The default configuration isn't usually what you want. Most of the time it's because you're building with debug, and by default Clang is statically linked, and by default it will use as many cores as you have in your system, and a debug version of Clang can come up to about 30 or 40 gigabytes in size. So if you're imagining, and your links, the working set size for the link gets to be about 6 to 7 gigabytes. So if you imagine you've got a multi-core machine and you'll do 7 gigabyte links at the same time, your machine is not going to like you very much. So basically, if you're going to use build with debug, make sure you turn the shared library on. And that's sort of something you can look at later. Okay. So here's what I came up with as a sort of the process for writing one of these Clang tools. So first thing here, the step one, it really is important to know what you want to do first. So this is a sort of a thing of, it's best not to sit down one day and say, hey, I'll write a Clang tool, because you'll get lost very, very quickly. There's an awful lot of different choice there. So what I'm assuming here is that you've got enough information about what you want to look for that you can write some test cases. And what I mean by these test cases, this is just like simple, maybe one function describing just precisely one little bit of source code that you're looking for. And then once you've actually got these tiny test cases, you can use the AST dump facility of Clang, and that will sort of basically dump out all the individual node names. I've got an example later on of what the actual output looks like, and you can use that to then say, these are the types of nodes I need to look for, and then you can look up just those nodes with the sort of AST matches. So what I'm sort of describing here is a very explorative approach rather than the theory-driven approach here, mainly because the theory-driven approach exceeds the capacity of my brain when you've got a program the size of Clang. So once you've found out the nodes that you want to match about, you then use the Clang query tool. So the Clang query tool is basically just a way of interactively putting in the Clang AST matchers, which I'll go into later. And once you've developed your AST matcher, which is like a domain-specific language for querying the AST, you can then import that directly into your C++ code, and then most of the work has been done for you at that point. Okay. So this is my toy use case. I'm not going to say that this is actually a very valuable one. It's just something that I wanted to use because it wasn't completely trivial. So what I'm thinking here is many code bases have literal parameters passed, particularly Boolean ones. It's actually very difficult to know what they actually mean at the call site. So, for example, some of them might be that true could be ignore a parameter or something like that, and you have no idea what that is at the call site. So some coding conventions say, oh, you should put a comment in to say what this actually means. So as I say, I'm not going to endorse that at all. It was just an example that I picked out the air. So I thought, why not I write a tool that will insert those comments for us? So that means what I've got to do is I've got to find all the call sites for which are using bool or integer literals. I've then got to look up the actual definition of that function and find the parameters. I've then got to write something that inserts that comment into the stream at the same time. So whilst it's not horrendously complicated, it's not completely simple either. Okay, so test cases. So what I recommend if you're going to do this, write a single test case per file, because the Clang AST dump gets very big very quickly, and try and avoid header files, particularly something like IOStream, because you will be there for hours picking through all of that. So once we've actually got that, we can then use our Clang query tool to develop the query. So one of the things that I mentioned here that you might need to know is that by default, these Clang query tools and all the other Clang tools will expect a compilation database. If you haven't got a compilation database and you've not got macros, then you just put -- at the end and it won't complain at you. Okay. So here's just an example of a C direct function call. So this is what the sort of process I went through to try and work this out. So just completely bog standard function call. And then we've got the function declaration. The important thing that I'm looking for here is there's a parm var decl, which is what our parameter is, and we have its name and its type over there. And then we have the actual call itself, call expr, and then you can see it's implicit casting to the type of the function to pointer decay, and then you can see it's got here the function f. Now the interesting thing here to look at here is this bit here, function f. I mentioned this now because on the next slide we've got something where we want to match this, but we don't want to match something that's on the next slide. So we could actually write something like that, which is a pointer to a function. And of course, the pointer to a function might have a bool parameter, but you can pass any function into that, and it might have many different names. So it's not really a very sensible thing to insert a comment into there. So I wanted to not match that. So here we have pretty much the same thing for f, but here we've got a decl exp not to function, but to the function parameter there. And of course, you can also see that the actual L value that it's going to call is not the actual function, it's the parameter that's being passed in. But anyway, that's by the by. But the main thing there was just, this is an example that I didn't want to match. Going a bit further, you've got some various other problems that you want to see. So this is often when you find part of the iterative process, you go through, you do your test example, and you go, oh, I didn't think of that. And then many of these things come out. So for example, if I pass 3, that's implicitly converted to bool. So I might have to handle that particular case. You can see here the implicit cast is in there. So I'm going to have to handle that in some way. Next slide, going a bit quicker. C++ member function. You'll notice that in the previous one it was call expr. Here we've got CXX member call expr and excluding the member there. That did come up. That did become quite important later on, particularly with this guy here, the operator, which you can then define to sort of make, I think, something that's called roughly a callable, and that uses the CXX operator call expr. And something that bit me when I was actually doing my C++ is that the actual decl exp for the actual class name here was actually in here. So when I actually looked at the number of parameters, I got it slightly wrong. So that was just something for a bit later. Okay, so what are my observations so far? things I need to start looking for are the nodes call expr, CXX member call expr, CXX operator call expr, bool literals, CXX bool literal expr, integer literals. And I'm going to have to look at casts. Won't go into too much detail right now because I haven't actually got a lot of time. So on to some more difficult things. So again, I wouldn't worry about this too much or any of the details. I'm just thinking that we've now just gone from basic C to the horrors of C++ plus templates. So some of these things you actually have to start experimenting with these to sort of work out, so just how does template instantiation work in the AST, and can I match this type of thing. You might also take the decision of my code base hasn't got all of this nasty C++ in it anyway, so I just don't need to worry about it. So if you're lucky, that will be the case. And if you thought these ones were bad, there's some even worse ones on this slide. And a couple of the ones here, I couldn't work out hand to handle. The one that I thought this one was particularly bad, where I've got a static function that's sort of defined in the struct, and I'm passing a function. I'm passing that as a template parameter there, and I couldn't quite work out how to distinguish that case in the AST. Anyhow, and that horror at the bottom is a variadic template function, which, and no matter what I tried, I couldn't stop Clang calling all of the functions args. Anyhow, okay. So this is just some observations on the template. So when you in the Clang AST, when you actually get to process it, you'll get to see the original template parameter, and you'll also get to see the actual instantiation. So I think in theory, once you get the instantiation, you can kind of track back through various bits of magic to find out that it did come from a template, but I found it quite difficult to do. Okay. So Clang AST matches. So this is the sort of magic that makes a lot of this actual possible. So I've got an example here of a line from that, and what that will do will match a record decal, which is either a struct or class, with the name my class, and then it'll bind it to an identifier called ID. And what we can do with that bound ID is we can look it up later in our C++ code. So again, won't go for too much of the details here because this is mostly taken straight from the Clang documentation from here. And they also, on that documentation, it has got an iterative scheme for just how to come up with your Clang query. Right, so Clang query is a really, really nice tool. So in effect, what all this, it accepts a simple domain-specific language, which is just those Clang AST matches. My recommendation, if you're going to use it, is to set the output to dump, which is just one command, because by default, if your Clang AST matcher fires, it'll just say matched at source line X or column Y, whatever. And that's not necessarily very helpful. But if you can get it to match on the actual AST block itself, that's really, really useful. So what the actual process to do this, again, this is verbatim from the tutorial. You look at the outermost class that you're looking for. That'll become a bit more clearer on the next slide. The AST matcher reference is a list of about 200 built-in AST matches that you can use. You create your match, verify that it works. You then look for the next inner part, keep on going until you're finished. Okay, I better start speeding up here. Okay. So this is my sort of thought process that I went through whilst I was developing my matcher. This sounds like it was straightforward, but it took me about 2 or 3 hours to go through this process. So what we need to do is find call sites with a bool or integer literal as a parameter, so we can insert the comment. So we need to find all the function calls with bool or integer literals as parameters, and we need to find the callee associated with this. And we don't want to match ambiguous cases, as I mentioned, with things like templates and function calls. So if we follow the process, call expr was our outermost class, and then we can sort of start refining that to look for has any argument, and we can use like all of, any of, to sort of, basically combine all of these little matches together. Okay, so my first attempt here, again, won't go for too much detail here. Call expr was my add one there, and any of, which is basically all of those bits. So basically saying, get me all the calls that have any bool or integer literal parameter. Okay, and you can see here it bound 1, and that's showing you the set member bound. Okay, so that's close, but it's not quite good enough because it basically matches too much. And again, won't go to the horrors of the details. That's what I ended up after 2 or 3 hours of trying to search through to find out ones that would get rid of some of the template matches. I wasn't able to get all of the thing, but I think that was close enough. So what I'm going to do now is to switch to C++. So the C++, you basically can just paste that straight in because that is actually C++. All that we need to do is to add some extra bind bits to pull things out. So one of the bits that I want to pull out the call expr, and I want to pull out the callee, and I can then refer back to that in my actual matcher. Okay, so this is basically just a bit of boilerplate. I'm going to skip this for time. It's pretty much, say, straightforward from the actual tool. So if you want to go through this later, please look back through it. Okay, so the following here is a bit of code just to sort of show what it is. I'll try and pull out the small bits, but I'm going to go through this very quickly. Details aren't actually that important. So this is basically the main function that you would have for almost any refactoring tool, and it's basically, Clang has got some additional helper functions that will process the source code database, and in effect all you're doing is you're launching this thing called a front-end action. So what our code that's going to be different from all the other is this front-end action. It's basically a C++ interface. Okay. So here's our front-end action. Most of this is just boilerplate, and what we're effectively doing is making a rewriter. The rewriter is where we put all our edits in, and then we create another class which is a AST consumer, and we're passing our rewriter to it. The rest of that interface is pretty much just boilerplate. The end source file action is basically a callback saying, I've finished processing the source file, dump all my edits. That's pretty much all that is. Okay, so AST consumer, there's our matcher, and it's basically saying, on the match, run a particular call. Let me think where it is. I can't quite remember here. There's I think, yeah, our call site matcher. So basically that call site matcher is just the class that we actually build to actually handle the callback. Now this is a little bit big, so I'm going to go through it again fairly quickly, pulling out the main points. That callee there is part of the bind expression that we had last time. So what I'm basically doing is getting the callee, processing through its arguments, storing them in a vector, so I've got the positions. Then I'm going to go down, I'm going to look at the caller, and I'm going to basically match each parameter that's an integer or a Boolean parameter, and then look it up in a vector to find its name. So it's actually fairly simple. Again, don't worry about that. You're probably not going to be able to see it anyway. I'm going to have to go through this a bit more thing. So here's kind of the tool in action, just on some of my test cases to show that it was actually working. There were some problems, as I can see, with variadic templates. I couldn't avoid all of the parameters coming out as args. Okay. So next bit, which I'm probably going to skip, which is basically how do I turn this into a Clang plugin? And all of this is just boilerplate. It's based, so you can follow this in the slides if you want to go through that. So why might you write something as a plugin? Well, basically it means you can fail a build. So if you have, say, an error that you want to introduce, you can write a Clang plugin, write an AST matcher to find it, and then error out on the build. But I'm going to skip that in the name of time. Okay. So conclusions. So I think writing your own Clang tool is feasible with about a week's worth of effort. That's about the time it took me to go through all the documentation, work out what I wanted to do, work out what problem I wanted to solve, go through the various iterative bits. I think it would be faster the next time around. If you're looking at online tutorials, you can get very, very far with those, but expect to have to find fix minor problems in the build system and various things due to things changing. You can save a lot of time by not handling difficult C++ template corner cases that you might not have anyway. If you can use a simpler tool, please do use a simpler tool. A lot of this is a bit of an overkill. And also think hard about maintenance. So if you're going to say, have a plugin that fails builds, you might have to have that as a part of your CI system, because you're not going to be able to unless you control what compilers everyone uses, you're not going to be able to force everyone to use a precise version of Clang that you're actually using. The other thing is, does this hit exactly the wrong sweet spot in that do you need to have a code base that's so large that the contributors don't know that basically haven't got the rules in their head? And do you need to have enough people willing to maintain this? In other words, do you need to have a code base as big as, say, Chromium or Mozilla before this approach becomes viable? That sort of thing. If you've got a C code base, you might be able to get away with simpler tools. Okay, so I say obligatory references there. I've lent very heavily on some of these. There's some very, very good material out this already, so if you do want to look at this, my best advice is try and find something someone that's done something very similar, and then modify it sort of by by experimentation to do that. Okay, so I haven't got any time to handle questions. I've only got about 15 seconds or so, but if anybody wants to come and talk to me, I'm here over the whole week. I'll be in the toolchain working room. I'm quite happy to talk about any of this. Okay, thanks very much.